Today's lesson is lesson 5.4, quadratic regression. Quadratic regression may be used to formulate the equation of quadratic functions. At least 3 points are needed to formulate the equation of a quadratic function using this method. The quadratic regression equation will be written in the form of y equals ax squared plus bx plus c, where the values of a, b, and c will be included in the graph's output. Remember, this form is called standard form. We can find the points on a graph as ordered pairs, from a table, or from descriptions. Quadratic regression may be used to model imperfect data that has a parabolic trend, but does not form a perfect parabola. In these situations, it is best practice to use all of the data provided to ensure a model with the best possible fit to the data. All right, so example number 1 says scientists are planning to launch an object straight up into the lunar atmosphere and analyze the time it takes for the object to fall to the surface of the moon. They compiled a data of values that they will accept to see when they run the experiment. We're going to go ahead and use the quadratic regression to write a quadratic function that can be used to model the expected relationship between the object's height in meters and the elapsed time in seconds. So over here in our little calculator instructions, I have gone ahead and written down for you the buttons that we're going to go ahead and push in our TI Inspire calculator to do this problem. Okay, I'll make a separate video on how to actually do that using this table and example 3's table. All right, so once we have all this data put in, this is going to go like for my X and this one's going to go for my Y. I'm going to go ahead and I'm going to write it in the standard form. What the linear regression is going to do is it's going to give me, oops, hold on. There we go, plus C. It's going to go ahead and it's going to give me a value for my A, and the value that the calculator will give me is negative 0.8125. It's going to give me a value for B, and the value that the calculator will give me is positive 10. And it's going to give me a value for C, and that value is positive 1. Now I can go ahead and I can write my equation. The y equals is going to be replaced this time with h of t from the table, right? Because this is my y. And instead of x, I'm going to use t. So I'm going to put in the a value, 125t squared, plus the b value, t, plus c. And there's my equation right there. All right, now I can go ahead and I can use this regression equation to predict the height after 12 seconds. So what they're telling me right here is that t is equal to 12. I could do this a couple of different ways. I could do this by actually substituting and using my calculator to do so. So I would plug in all this stuff that I'm going to write down with the laser. I could go ahead and plug this into my calculator and hit equals, and the calculator would tell me the answer. Or I could type this into my equation, and then I could do Control T inside my Inspire, and I could find my answer. Either way, I'm going to find the answer of 4. This would be 4 meters above the surface of the moon. It's always good to go back and to understand what that 4 means, because sometimes you will be asked to do this on the test and you have to explain what it means. So remember, we're solving this number for this column, so I have to know what this means, what that means in this relationship. All right, in example 2, what we went ahead and we did was we wrote the equation based off of this graph. Now, this is some species of penguins can jump many feet above the surface of the water to jump onto an ice cliff. The relationship between the vertical distance height in feet y and the horizontal distance in feet x traveled by a penguin jumping out of the water onto the cliff of ice is shown in the graph. What we went ahead and did was we went ahead and we took our 3 points, because remember, to do linear regression, we need a minimum of 3 points. This one right here is 0, 0. This one right here is 2, 8. Remember, you're going down to x and then over to y. So this one would be 4, 8. And we went ahead and we plugged them in. Remember, all of these will go into the same first column for my x values, and then these ones are going to go in for my y's. Yes, I'm going to put the 8 in twice. And now I'm going to go ahead and I'm going to write down my formula. I was given a -1 for my x. I can just use that as a negative. I don't have to put the 1 with it because it can be considered invisible. This is very common, but it's not incorrect to have the 1 with it. My B value was +6 and my C value was 0, which means I could have this, but because I'm adding nothing, it doesn't actually have to be there, so I can just make it disappear. I do want to quickly just talk about the domain because we did do that in class. And the reason I wanted to talk about the domain of this one, because this one's domain is not all real numbers due to the fact that there are points at the end of my graph and not arrows. So I had to go ahead and read my graph from the left over to the right side of my graph, making my left wall and my right wall. So my left wall would go right here through this point, which has an x value of 0. So I would start my domain with the number 0, and I would use the less than or equal to symbol. I would choose the variable x because this is the variable for domain, and I would use less than or equal to once again. Now I'm going to go ahead and read over here to the right side of my graph. This is the last point on the right side of my graph, so this is where I'm going to put my wall. The x value of that point is 4, and so this is the number that I would use for the domain. Identifying key attributes from the graph. The graph of a quadratic equation using technology. We're going to adjust the window to a reasonable values so that we can view the function. And we're going to use the calculator commands to identify the zeros and maximum or minimum values, which of course, remember, are the vertex. All right, so the height of an object launched into the air in relation to time is modeled by a quadratic function. The object was spotted at 448 feet 1 second after launch, 464 feet 2 seconds, 320 feet after 5 seconds, and 208 feet after 6 seconds. The first thing I'm going to do is I'm going to take all those numbers and I'm going to put them into the table. I'm going to go ahead and put the seconds on top, 1, 2, 5, and 6, and then I'm going to put their corresponding feet on the bottom for the height. Oops, hold on a second. There we go, and 208. Okay, in part B, I'm going to go ahead and use my regression function on my calculator to formulate the quadratic model that represents the height of the object to the time elapsed since it's launched. Remember, now normally we would probably use t for time. I'm going to go ahead and make it x, and height we could use h of t, but I'm going to go ahead and use y because they're more commonly used. So I'm going to go ahead and once I've done the regression, this is what my calculator is going to tell me. Remember, it's going to give me an A value, a B value, and a C value. So it gave me an A value of -16. It gave me a C value or B value of +64, and it gave me a C value of +400. Now I'm going to go ahead and I'm going to graph that regression model. To graph the regression model, I'm just going to take these points right here and I'm going to do my best to plot them here in the graph. So let's see. From the model, I can get my y-intercept, which is here at 0 and 400. So I can go ahead and plot 0 and 400. And then I could come in and plot all these points. But what I did, what actually worked a little bit better because it wasn't quite as well, I'm going to go ahead and do 2 and 464. So I did the best I could to just put it where I thought 464 would be. And then I could try to do the 5 and 6. I mean, I could put them if I wanted to, right? Let's see, 320 maybe right in there. And then from my graph, I can see that it's going to have an x-intercept of 7.385, 0. So I can now go ahead and I can graph that. Let me try the best I can with my graphing feature here. Let me try to get it a little bit better. Oops, no, go back. Ah, shoot. There we go. I'm going to go ahead and I'm going to just erase that point right there. Oh yeah, because it was 5. That's why it was off a little bit. So 5 should be in between 5 and 320. There we go. That looks better. Make it come back. All right. Use the graph of the regression equation to predict how much time will elapse between the launch and when the object will hit the ground. Well, hitting the ground would be at 0 feet, so this would be hitting the ground. So I'm going to go ahead and use that x-intercept, about 7.385 seconds. What is a reasonable domain for this model? Remember, once again, this model does not have an X or a Y. It doesn't have arrows, so it's not going to be all real numbers. So I'm going to go ahead and say less than or equal to x, less than or equal to. I'm going to go ahead and I'm going to get my left wall. So I'm going to go to the left side of the graph and I'm going to find the very first point, and this is the wall that I'm going to put, and I want the x value from it 0. So I'm going to go ahead and put 0 right here. And now I'm going to go ahead and read over to the right side. This is my last point on the right side. This is where my wall would go up. I would use this number right here because it is my x value. If we were to state this in seconds, it would be between 0 seconds and 7.385 seconds. All right, now let's go ahead and use the graph of the regression equation to determine the maximum height reached by the object. When did the object reach its maximum height? So the maximum height would be considered right here at this point, which is my vertex, my maximum of my parabola. What this means is that it reaches the max height of 464 feet after 2 seconds. Or you could say after 2 seconds, it reaches a maximum height of 464 feet. All right. Our last example today, example 4, has the average monthly temperature in College Station, Texas, can be modeled by a quadratic function. January equals month 1, February equals month 2, etc. So March, April, May, June, July, August, September, October, November, December. That's what those numbers mean. These are the average temperatures for each of those months. Formulate the equation that models the data. So once again, we put this into our calculator, and our calculator gave us our A, B, and C values, and we're going to go ahead and we're going to write down the equation. Remember, I will go ahead and show you how to do that in class, and I will more than likely record another video to show you how to do this in the calculator. But there's my A value, my B value, it was positive, and my C value, it was positive as well. Remember, if my B or my C value were negative, these positives would change to negatives, right? These positives would change to negatives if it was a negative value. I can now go ahead and answer part B. The table shows that the average monthly height in March, or average monthly high in March, is 73 degrees Fahrenheit. Compare this value to the March average high temperature predicted by your regression model. So this is what they're doing, right? So we're going to plug 3 in for x. So we could just go into our calculator and plug in negative 1.0883 squared plus 14.933 times 3 plus 40.864, and we could go ahead and press enter and the calculator would give us an answer. Or remember, we could go ahead and put this into our graph, right, into our graphing feature, and then we could press Control T and we could go look at x equals 3 in the table and it should give us our answer. The answer that we found from the regression model was this. Let's see, 75.8, and then it would have the same unit degrees Fahrenheit. What we're noticing right here is that our answer and the answer from the data are nearly 3 degrees apart. Notice it's 3 and 5, that's 2, but then this 0.8 is almost a whole nother degree. Our regression model is about 3 degrees Fahrenheit more than our data, which isn't really bad.